Okay, from this time, then I will talk about the two-particle system in one-dimensional two-particle system. And then let's consider two particles bound in within the one-dimensional potential energy well. One-dimensional potential energy well, and here we consider two particles on the one-dimensional potential well. We already know that the potential well of the single particle, the solution is already studied in undergraduate course. So then one-dimensional single particle Hamiltonian is that the single particle Hamiltonian is the kinetic energy plus potential energy. Here we already know that the eigenvalue problem for Hamiltonian, single particle Hamiltonian, and the wave function. Wave function is that energy eigenvalue and eigenfunction. So we should solve the eigenvalue equation. Then here we consider for a two-particle system. Here two-particle Hamiltonian is that first particle Hamiltonian is that the P1 square plus second particle kinetic energy square plus potential energy Vx1 plus Vx2. Here we do not consider for the interacting Hamiltonian between two particles. Only here we this separate potential. It means that we do not consider interacting particles. It is identical particles, are identical and independent. Also, there is no spin dependent. There is no spin information. So only the special function. So there is no spin dependence also. So the potential is separate. And the interacting Hamiltonian can be considered later. At first, if we think that just only the two-particle system, and the two-particle eigenvalue equation is that h psi and the h1, x1 and x2 equal to e psi x1 and x2. Then the one particle at x1 and the other particle at x2. And the two-particle probability density two-particle probability density can be calculated from the square of the wave function x1 and x2 and square and integrate with the dx1 and dx2. That is that it is a probability of finding the particle at particle 1 at x1 and the other particle at x2. So it is the probability of finding of particles of two independent particles. So and we should think that the symmetric superposition symmetric superposition means that the space part, the spatial part wave function has two properties. One is that the symmetric wave function, the other one is the antisymmetric wave function. For example, in this case, and symmetric wave function is the normalization constant, and also A particle at x1 and the B particles at x2, and it is symmetrically connected, and plus A particle at x2 and B particle at x1. It is exchange of two particles. So, and A particle at x1 and B particle x2, and it can be symmetrized between the x1 and x2. So, and A particle at x2 and B particle at x1. So it is, but in general, you know, and these quantum mechanical particles is identical particles. So we do not. It is not possible for distinguish for two particles. But anyway, then let's start from the distinguishable particles. In other case, it is a symmetric superposition because if we think that if there is two particle exchange, then it is a wave function. The sign of wave function do not change, and it is identical. So it is a symmetric with the exchange of two particles. But in the antisymmetric superposition, or special part antisymmetric superposition is that NA means the antisymmetric normalization constant, and also phi NA at x1 and phi NB at x2 and minus phi NA x2 and phi NB x1. In this case, when we exchange between two particles, A particle at x1 and B particle at x2, and the A particle at x2 and B particle at x1, but when we exchange with each other, then the exchange makes that a minus sign appears, because it becomes here and it becomes here, so and the minus sign appears. So when we exchange of two particles at x1 and x2, then it makes that exchanging two particles makes that the minus sign, so it is antisymmetric superpositions. So for exchange two particles, the energy in both symmetric and antisymmetric case, and the NA and B case, and it is summation as the NA plus NB. So and the NA and NB means that quantum level, quantum energy level at each particles. So at here, it is a general description. So let's restrict our discussion on the two particle at ground state. Two particles at ground state. Ground state means that it is A particle and B particle, and there are energy levels like this, and 1, 2, 3 energy level, and also at ground state, and it is resides at the ground state. So here E1, E2, E3, then the two particles at the ground state. So Na also at E1 and the NB also at E1. So in the ground state energy, it is at one state in both particles. So it is a 2E1 case. So and we think that the symmetric wave function, symmetric two particle wave function, at ground state, and the psi 1 state as symmetric x1 and x2 is that the multiplication of two particles x1 and x1 at energy level 1, and psi x2 also resides at the energy level 1. So it is a 1-1 case. This is a symmetric because two particle exchange at x1 and x2 and it is identical. For example, Na exchange at Nb site and the Nb site and at Na is identical, and so it is a symmetric. Then antisymmetric case, antisymmetric two particle system, two particles wave function. In this case, and we already studied for the bosonic wave function and the fermion wave function. It is one state and antisymmetric case x1 and x2. So it is a wave function in the above. So and basically in the symmetric superposition makes that basically this term and this term is identical. So it is a normalization. Normalization can be a factor. So and the symmetric superposition case in above case, and it can be written down like this. But in antisymmetric ground state, at one state at x1 and one state at x2, and it is antisymmetric. So when you write down here in Na and phi 1 x1 and phi 1 x2 and minus phi 1 and x2 and phi 1 also x1. So it means that it is two term, it becomes a zero. So antisymmetric two particle system, the wave function is zero. It means that there is no probability of having an antisymmetric wave function. So it means that no probability of having an antisymmetric wave function. So, and in this case, we do not consider for spin. But in general, we should consider for the spin state. So let's consider for the spin state. For example, for two spin zero bosons, in the bosonic particles case, and spin and corresponding spin magnetic quantum number is that 0 and 0 case. It is coupled basis. In uncoupled basis, and S1 and S2 and M1 and M2 in both cases, and the 0 0 spin, so magnetic quantum number and the 0 0. So it is uncoupled basis and the coupled basis in a spin 0. Clearly it is a symmetric wave function, and so in bosonic cases and psi 1 1 it is symmetric because and the wave function 1 1 x1 and x2 it is symmetric, and the spin also symmetric because in the above case, in both fermion and bosonic case, antisymmetric special wave function is 0. So there is no possibility of the antisymmetric wave function in the special part. So and the special part wave function should be symmetric. Here and because bosonic case is a spin quantum state, it is symmetric because it is a 0 0. It is a symmetric wave function, symmetric spin function, symmetric spin vector. So it is a symmetric. It means that the symmetric total wave function in bosonic case. How about it is a boson case? How about two fermions? Two fermions case. Two fermion case basically, and also one state is a spin up and spin up. It is a spin up and spin up case. So spin up case for two spin up makes that total spin is 1, and corresponding total spin 1. So total spin 1 case, and the magnetic quantum number can have the 1, 0, and minus 1. There are 3 possibilities. So minus 1 means that the spin is down state. And spin 0 means that it is symmetric, because, and here it is symmetric because 2 spin up case, if we exchange 2 particles, then it is symmetric. So it is a symmetric spin function. And also minus 1 minus 1 also spin down. If we exchange 2 particles, then also it is symmetric. So 1, 0 should be symmetric. 0 means that the spin up and down combination, but it should be symmetric. So it is normalization factor is 1 over square root 2, and also it is spin up down combination with a plus minus up. And so we call it is a spin triplet state, because it is energetically identical. It is a degenerated state. It is a symmetric spin vectors. It is a symmetric spin vectors. On the other hand, and 0 means that the spin up and down, and it can be anti-symmetric spin vector. So it is 1 over square root 2, and also spin up and down can be combined with a minus sign, minus plus. Then it is we call it as a singlet state, because there is only one spin state, singlet state, that is anti-symmetric. It is anti-symmetric spin function, and spin up and down combined with the minus sign. So, for example, in the triplet spin state, and the because it is a symmetric spin vector. So, and because fermion case total wave function should have the anti-symmetric, and it means that anti-symmetric spatial wave function. So anti-symmetric spatial wave function, as we discussed in the above, and should be 0. Anti-symmetric spatial wave function should be 0. So, and psi anti-symmetric 1 state x1 and x2 equal to 0. It means that it is a Pauli exclusion principle, and so it means that the ground state wave function of 2 particles, the probability is 0, and so there is no possibility of the 2 particles can occupy in the same quantum state of 2 particles. It is a Pauli exclusion principle. Two particles with the same spin cannot be occupied in a same quantum state. So total wave function for ground state should have the triplet state. Triplet state is not possible in the fermions in the ground state. So only the symmetric spin state, anti-symmetric spin state. So it is a spin singlet should be. And also spatial wave function should have the symmetric x1 and x2. So it is that phi 1 x1 and phi 1 and x2 and 0 0. It means that spin singlet in a quantum state, it is possible in a single ground state. ground state can occupy the spin up and down